Train rails are among the most critical pieces of infrastructure in the modern world, carrying millions of passengers and billions of tons of freight across continents every single day. Yet few people ever consider the immense industrial effort required to produce rails that must remain perfectly straight, incredibly strong, and reliable under decades of constant stress. A single rail must withstand crushing axle loads, extreme temperature swings, vibration, weather exposure, and non-stop metal-on-metal contact without deforming or failing. What appears to be a simple steel beam is actually the product of one of the most demanding metallurgical manufacturing processes on Earth. And today on The How Factory, we're going inside steel mills to see exactly how train rails are made, from molten steel to flawlessly straight tracks laid across the world. The process begins with raw steel production. Rail steel must meet far stricter standards than ordinary construction steel, requiring precise control over carbon content, hardness, toughness, and internal structure. The journey starts in blast furnaces or electric arc furnaces, depending on the mill. In blast furnaces, iron ore, coke, and limestone are layered into towering structures and heated to extreme temperatures exceeding 1,500 degrees Celsius. Chemical reactions strip oxygen from the iron ore, producing molten iron. In electric arc furnaces, recycled steel scrap is melted using powerful electric arcs. Both methods produce liquid steel, which then undergoes refining. Once molten, the steel is transferred to ladles where its chemistry is adjusted. Alloying elements such as carbon, manganese, silicon, and sometimes chromium are added in precise quantities. Carbon content is especially critical. Too little and the rail will wear quickly. Too much and it becomes brittle. Oxygen is removed through deoxidation, and impurities like sulfur and phosphorus are reduced because they weaken steel under repeated loading. Sensors and laboratory tests constantly analyze the molten steel to ensure it meets rail-grade specifications before casting. Next comes continuous casting, where molten steel begins to take solid form. The steel is poured into water-cooled copper molds that shape it into long rectangular beams known as blooms. As the steel cools from the outside inward, it solidifies into a dense, uniform structure. The blooms exit the caster glowing red-hot and can be tens of meters long. At this stage, the steel still contains enormous internal heat and energy, which will be used in the next steps rather than wasted. The hot blooms are transported immediately to the rolling mill. Timing is critical. If the steel cools too much, it must be reheated in massive furnaces that consume enormous energy. In many modern mills, continuous casting and rolling are directly linked to maximize efficiency. Reheating furnaces bring blooms to precise rolling temperatures, ensuring the steel is soft enough to shape without cracking. Rolling is where the rail's iconic profile is formed. Blooms pass through a series of heavy rolling stands equipped with massive steel rollers. Each stand progressively shapes the steel, reducing thickness and forming the distinctive railhead, web, and base. This process requires extreme force. Rollers exert thousands of tons of pressure as they squeeze and stretch the steel. The shape becomes more refined with each pass. Sensors monitor dimensions continuously, making micro adjustments to ensure the rail profile stays within tolerances, measured in fractions of a millimeter. As the steel is rolled, its internal grain structure is elongated and aligned, dramatically increasing strength and fatigue resistance. Rolling also improves toughness, allowing rails to absorb repeated impacts from train wheels without cracking. The rail exits the final rolling stand at speeds that can exceed several meters per second, glowing orange-hot and stretching hundreds of meters long as a continuous strand. Immediately after rolling, the rail enters controlled cooling zones. Cooling is one of the most critical stages in rail production. If rails cool too quickly, internal stresses form that can cause warping or cracking. If they cool too slowly, the steel may lack sufficient hardness. Specialized cooling beds use controlled airflow and timing to cool rails evenly along their entire length. Some high-performance rails undergo accelerated cooling or heat treatment to increase surface hardness while maintaining a tough core. Once cooled to manageable temperatures, the rails are cut to length using high-speed saws. Standard rail lengths vary depending on application and country, but modern rail sections can exceed 100 meters. Longer rails reduce the number of joints on tracks, improving ride quality and reducing maintenance. Each cut must be perfectly square to ensure proper alignment during installation. At this stage, rails may look straight, but microscopic imperfections remain. Straightening is therefore essential. Rails pass through roller straightening machines that apply controlled pressure at specific points along the length. These machines detect bends measured in fractions of a millimeter and correct them precisely. Straightness is critical. Even slight curvature can lead to track instability or accelerated wear once installed. After straightening, rails undergo surface treatment. The rail head, the top portion that contacts train wheels, may be ground or milled to achieve the correct surface finish. This improves wheel-rail contact, reduces noise, and minimizes wear. Some rails receive head hardening treatment, where only the top surface is reheated and rapidly cooled to increase hardness while leaving the rest of the rail tough and flexible. This process dramatically extends rail life in high-traffic corridors. Quality control intensifies after shaping. Each rail is inspected using multiple non-destructive testing methods. Ultrasonic testing sends sound waves through the steel to detect internal cracks, voids, or inclusions invisible to the eye. Eddy-Current testing checks surface integrity. Laser measurement systems verify profile accuracy, straightness, and dimensional consistency along the entire length. Any rail that fails inspection is removed immediately. There's no tolerance for hidden defects in rail infrastructure. Chemical and mechanical testing continues alongside inspection. Samples from each production batch are cut and tested for hardness, tensile strength, impact resistance, and fatigue performance. Rails must withstand millions of load cycles over decades without failure. Some samples are bent, struck, or subjected to simulated wheel loads to confirm performance under extreme conditions. Once approved, rails move to finishing and marking. Identification marks are rolled or stamped onto the web of each rail, indicating steel grade, production date, mill origin, and batch number. These markings allow rail operators to track performance and maintenance history throughout the rail's service life. Protective coatings may be applied to prevent corrosion during transport and storage, especially for rails shipped long distances or stored outdoors. Rails are then bundled for transport. Handling rails is a logistical challenge due to their length and weight. Specialized cranes and automated stacking systems align rails precisely to avoid bending. Bundles are secured with heavy steel straps and placed onto rail cars or flatbed trucks. Longer rails may be transported using specially designed rail carriers that support the entire length to prevent sagging. Behind the scenes, safety is a constant concern in rail manufacturing. Steel mills operate with extreme temperatures, heavy machinery, and moving loads weighing hundreds of tons. Automated systems, remote-controlled equipment, and strict safety protocols protect workers while maintaining high output. Sensors monitor equipment wear and temperature continuously, triggering shutdowns if abnormalities occur. Environmental control is also increasingly important. Modern rail mills recycle steel scrap back into production, reducing the need for raw iron ore. Waste heat from furnaces is recovered and reused. Water used in cooling and cleaning is filtered and recycled through closed-loop systems. Dust and emissions are captured using advanced filtration to minimize environmental impact. What makes rail manufacturing remarkable is the balance between brute force and extreme precision. Massive rollers and furnaces shape glowing steel with incredible power, yet tolerances are measured in microns. Rails must be strong enough to support thousands of tons, yet flexible enough to expand and contract with temperature changes. They must endure vibration, weather, and constant impact without losing alignment. From liquid steel glowing inside ladles to perfectly straight rails stretching across continents, the journey of a train rail is a triumph of industrial metallurgy. Every kilometer of track depends on the consistency and reliability forged inside these mills. Without this process, modern rail transportation simply would not exist. And that is exactly how train rails are refined, cast, rolled, heat-treated, straightened, inspected, and shipped, transforming molten steel into perfectly straight tracks that carry the world's trains safely and efficiently every day. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines, materials, and processes that power global infrastructure.